This is going to be something that we take 2 days on. So today's it's just going to be singular chain rule, and then tomorrow we're going to do double and triple chain rule. I know that sounds like a ton of fun to all of you. Okay, so first I want to start with a simple practice. So I would like you to find the derivative of each of these functions. So the first one is y equals sine of x, and the second one is y equals x squared minus 4. I would like you to find the derivative of each of those, just really, really quick. Okay, Corbin, what's the derivative of sine of x?
Cosine of x.
Deanna, what's the derivative of x squared minus 4?
2x.
2x. Right? So each of those is simple enough to compute the derivative of. But what if I changed it a little bit? For instance, what if I made our original function the sine of x squared minus 4? So what I did is I took this function and I put it inside of the sine of x function. So I essentially created a composite function. Could I just do the derivative like I did before? What do you guys think? The correct answer is no. We cannot just do the derivative like we did before because they're not two separate functions. They're a function within a function. So somebody with way too much time on his hands figured out that we can take the derivative of these composite functions using something called chain rule. So on chain rule, when we have a composite function, and this only works on composite functions, this means that I have a function g inside of a function f. F is always the outside function and g is always the inside function. When I go to take the derivative of this, I take the derivative of the outside, leaving the inside the same, and then multiply by the derivative of whatever that inside function is. So I would say that the derivative of f of g of x is f prime of g of x times g prime of x. I know that sounds super duper confusing, but when we put numbers with it, it might not be so bad. Okay, so make sure you have this written somewhere because it's super duper helpful to have. The easiest way to learn these is to jump right into an example, so that's what we're going to do. The first example that I would like to do is y equals 9x to the 4th plus 6x squared plus 1. So as you're writing this, you're probably going to think to yourself, hey, this is just a power rule problem, right? It's not a chain rule problem. But I specifically picked this one because if I were to factor this, it would factor into 3x squared plus 1 all squared. So this is the same function represented two different ways. This is going to allow us to check to make sure that the derivative we're getting with chain rule is the same as the derivative we would get with power rule, okay? So we're gonna do the power rule portion first, and then we'll come over and do the chain rule portion. So what is gonna be the derivative of this 9x to the 4th plus 6x squared plus 1? Brock.
36x cubed plus 12x.
Right? Super easy. So what should happen is that when we take the derivative of this one using chain rule, it comes out to be the same as this derivative, okay? That's why I set this one up the way I did. So now let's do the chain rule portion of this. When I'm doing chain rule, one way is to identify the inside and the outside functions. So that's what I'm gonna do. F is my outside and G is my inside. Pretty much anytime there's parentheses in a chain rule problem, it's going to indicate that parentheses and out is your outside function. So here, my outside function F is the parentheses squared. It doesn't matter what's in the parentheses. I'm only caring about the parentheses and the exponent part of it. Which means if I were to take the derivative of this, it would just be power rule. I would drop my exponent out front and then reduce my exponent by 1. So the derivative of this F is 2 times whatever's inside the parentheses, all to the 1 power. And you don't necessarily have to put that 1 exponent there if you don't want to. Okay, so that was just the outside portion. Now I need to identify my inside function and its derivative. So my inside function then is anything that's inside the parentheses. So here there's going to be 3x squared plus 1. And its derivative is a power rule problem. So I drop the 2 to make it 6x. And that's it. Okay? So I have my original F and its derivative, and I have my original G and its derivative. I'm going to plug those then into this derivative pretty much formula that we have for chain rule. So that means I'm going to have the derivative of F with the original G times the derivative of G. I know my derivative of F was 2 parentheses to the 1 power. The original G then that goes inside was 3x squared plus 1. And then times my G derivative, which was 6x. From here, I just need to simplify. So I get 2 times 3 is 6x squared plus 2, all times the 6x at the end. Distribute that in. I get 36x cubed plus 12x, which matches the derivative I got from power rule. Make sure you guys can see that. Anybody super duper confused by the chain rule part of this? Okay, so if you're given a problem like this, you're more than welcome to multiply it out and just do power rule, unless I have explicitly said use chain rule to solve this. Sometimes chain rule makes it harder. Sometimes chain rule makes it easier. It's just another avenue of solving a problem. Okay? Of course, we're going to go ahead and do another one. So the next example I would like to do is y equals sine of x squared plus x Once I have the function written, just like before, I need to identify my outside function and my inside function. So it's pretty obvious to me that my outside function f is sine of the parentheses, and my inside function g is what's inside of the parentheses, so x squared plus x. Then I'm going to go ahead and calculate the derivative of each of these. So the derivative of sine is cosine, and the derivative of x squared plus x is 2x plus 1. Once I have those 4 things, I can go ahead and write my derivative function. So remember, for chain rule, it's f prime of g times g prime, where my f prime here is cosine parentheses. Inside the parentheses is my original g, which is x squared plus x, times the derivative of the inside, which is 2x plus 1. I can't really do anything to simplify this one except for to bring, I could go ahead and distribute actually all of this to the 2x and to the 1. So when I do that, I get 2x cosine of x squared plus x plus cosine of x squared plus x. So I just went ahead and distributed this entire first function to each of the values inside that second parentheses. On each of these, I expect that you are going to simplify this as far as it can go, okay? Anybody super duper confuzzled? Okay, let's do another one. This time I'm going to call on some of you to answer some questions. So make sure you're ready. This next example is y equals cosine of 3x plus pi. Corbin, what's my outside function?
Cosine.
Okay, cosine of the parentheses, right?
Yes.
Then what's its derivative?
Negative sign of parentheses.
Negative sign of the parentheses. Guzman, what is my inside function?
I know that the 3x goes to 3, but does pi just stay pi or does it go to 1?
Okay, hold up. So first, you recognize that the inside is 3x plus pi, right?
Yeah.
And you know that the 3x goes to 3. What is pi? Is it a variable or is it a number?
A number?
It's a number, right? And the derivative of any number is just 0.
Number.
So the derivative of 3x plus 5 is just going to be 3. Or sorry, plus pi is just going to be 3. That's a really good question, and they do like to throw pi in there in hopes that it will confuse you, okay? So when it comes to things like pi or the square root of 2, just remember those are numbers, and the derivative of any number is just 0, okay? So then from here, my overall derivative would be negative sine of 3x plus pi all times 3, which is the derivative of that inside function. So then I call this combining stragglers. I don't want to leave this 3 out here. I want to combine it with what's in the first parentheses. So this then would equal negative 3 sine of 3x plus pi. And then we're done. Any questions, concerns, or issues so far? The more you do this, the less you always have to write this out. So if you're super comfortable writing out the whole inside and outside and derivatives, you're absolutely welcome to do that. But the more you do this, the more you'll see that we're just taking the derivative of the outside, leaving the inside the same, and then multiplying by the derivative of the inside, which sometimes just makes it a little bit faster. Okay? So let's go ahead and do the next one. My next function is y equals tangent of 2x minus x cubed. You are more than welcome to do the inside-outside thing again. I'm just going to go ahead and do it straight across. So when I take the derivative of this, I first take the derivative of that outside function tangent. What's the derivative of tangent? Secant squared, and where the x is where I place that inside function. So I have secant squared of that inside times the derivative of 2x minus x cubed, which is 2 minus 3x squared. I can't leave it like this. I need to simplify it. So I'm going to distribute this whole secant squared of 2x minus x cubed to each of the values inside of that second parentheses, which is going to leave me with 2 secant squared of 2x minus x cubed minus 3x squared secant squared of 2x minus x cubed. So when we multiply by something and we have a trig function, that number that we multiplied by just comes to the front. And then this would be simplified. As far as you can, yes.
Are we gonna have to simplify it?
This one is as far as we can go. There's not really a whole
So how
lot we
would
can do with
simplify
it,
this one?
but you will see in some later examples, the ones that we can simplify, we do. So by expanding it, you've technically simplified it.
Okay.
So this one is good.
Okay.
Anybody super confused on this one? So you would have gotten the same thing if you had done the inside function and the outside function and taken each of their derivatives and put them in the formula. It would have come out to the same answer. Okay, so let's go ahead and do another one. Overall, is this better or worse than you thought it was going to be? Better. Anybody else? Better? Okay.
Better.
That makes me happy. Next example, y equals 5 cotangent of 2 over x. As we're looking at this, there's something that I just don't like because it's going to make my life a lot harder. Can anybody tell me what that is? Nope, I like the 5. The 5 is just going to stay out front.
Is it the
Doesn't really
5?
hurt anything.
The fraction.
The fraction. So we can actually rewrite that so we don't have to use a fraction, which means we don't have to use quotient rule. So this is the same as 5 cotangent of 2 times x to the negative 1. So when I brought it up to the numerator, it just made its exponent negative. And now that inside is a power rule instead of a quotient rule, which makes it so much easier. Which means I can now take the derivative. So when I take the derivative of the outside first. What's the derivative of 5 cotangent?
Is it -5 cosecant squared?
Yes, -5 cosecant squared, because the derivative of cotangent is negative cosecant, and the 5 has to stay with it. So this is -5 cosecant squared of everything that was originally inside the parentheses times the derivative of what's inside. So what's the derivative of 2x to the negative 1? Power rule, bring the negative 1 down and it becomes a negative 2x, and then we decrease it by 1, so our exponent becomes a negative 2. So then from here, I like to put my stragglers together. So I'm going to multiply this in with the -5 that's already up there, which means I get y prime equals -5 times a -2 is a positive 10. X to the negative 2 times cosecant squared of 2x to the negative 1. When we're simplifying like this, I can't leave negative exponents. So because this is all being multiplied, this x to the negative 2 is going to move down to the denominator. Which now makes my 2 positive. And then I can replace 2 times x to the negative 1 with 2 over x, and then I'm done. Oh, goodness. Questions, concerns, or issues with that one? Okay. Is everyone done writing that one? Or is anybody still writing that one? Okay, next example. Okay, so now I have y equals secant of tangent of x. On this one, I'm going to formally write out the outside and the inside, and you'll see why, just to avoid some confusion. And then from there, like it shouldn't be that difficult to finish, okay? So what's my outside function here, Wackle?
Secant and then the parentheses.
Perfect. So what's the derivative of secant?
Secant x, tangent x.
Right. So it's secant of parentheses times tangent of parentheses. Because instead of having an x here, I have another function. So the derivative of secant is secant tangent and then whatever's inside the parentheses in place of x. My inside function is tangent of x. And what's the derivative of tangent? Anybody?
Secant squared.
Secant squared. And then it is of x because I had an x in my tangent. So then from here, I just do my derivative. So the derivative is the derivative of the outside with the original inside. So that means it's going to be secant of tangent of x times tangent of tangent of x. And then all of that times the derivative of my inside, which was secant squared of x. There is no way to really simplify this one at all, so we just write it all as one big problem. So we have secant of tangent of x times tangent of x times secant squared x. And it is all one multiplication problem.
Why wouldn't it be a secant cubed?
Because what's inside of them is not the same.
Okay.
That's a really good question though, because there are times where we can do that, but only if the function on the inside is also the same. Same thing, tangent of x is not the same as tangent times tangent. That is not the same thing because they don't have the same inside functions. Okay, so please do not try to write this as tangent squared x. Don't do it. Any other questions on this one? Okie doke, let's do another one. This time I have the quantity cosecant x plus cotangent x, all taken to the -1 power. So when I go to take the derivative of this, I do the derivative of the outside first, which is the parentheses, and then the exponent -1. So what's the derivative of parentheses with an exponent 1 on it?
-1 parentheses -2.
Perfect. So the exponent drops out front, and then we decrease our exponent by 1, keeping the inside the same. So it's -1 times our inside cosecant x plus cotangent x, all to the -2 power, and then times the derivative of that inside. Okay, so it is addition, which means it's going to be simple individual derivatives that I will then add together. What's the derivative of cosecant of x? Come on, it's in your notes.
Negative cosecant of x, cotangent of x.
Perfect. So this is going to be negative cosecant x, cotangent x, and then plus, what's the derivative of this cotangent x that I had in my original inside?
Negative cosecant squared of x.
Perfect. Okay, so this is originally what my derivative looks like. So we did the derivative of the parentheses with the exponent -1, which dropped out front, and decreased our exponent by 1. Then we did the derivative of the sum of the two trig functions on the inside and multiplied that in. So from here, all that's left to do is reduce. The first thing I'd like to reduce is I'd like to bring this whole parentheses to the -2 power and move it down to my denominator, which is going to make it to a +2 power, which is going to look a lot nicer. So when I do that, I'm going to take this -1 and I'm going to multiply it into each of these terms in that second parentheses, which will in turn turn both of those positive. So now I have positive cosecant x cotangent x plus cosecant squared x in my numerator over cosecant x plus cotangent x, all to the +2 power in my denominator. I am not finished, however, because I can reduce this farther. So I notice in that numerator that if I were to take a cosecant out of each of these two terms, I'm going to be left with cotangent x plus cosecant x, which is going to match one of the factors from my denominator, which is going to allow me to cancel them out. So then this becomes cosecant x times cotangent x plus cosecant x over cosecant x plus cotangent x squared. Even though these are in opposite order, because it's addition, they're still the exact same thing, which means that this whole parentheses from the numerator cancels out one of my factors from the denominator. So it's no longer raised to a power of 2, and I was able to cancel out this top one, which allows me to simplify this into cosecant x over cosecant x plus cotangent x. And then I'm finished.
Wait, what happened to the squared and the cosecant squared?
I took a cosecant out of it and I put it out front
How?
because this had a cosecant and this had a cosecant. So I just took one out of each of those and I put it out front. So I basically divided it out.
Okay.
So when I took it out of this one, it just left the cotangent. And when I took it out of the cosecant squared, when I take away one of those, it just leaves me with one left.
Okay.
These are the ones that you can simplify a lot farther. Okay, so if you get one like this on your homework, which you won't, I'm not that mean yet, I expect you to simplify it as far as it can go. Questions? Is anybody still writing this one? Okay, let's do another one. We really only have 3 examples left. for today. Okay, so our next example is y equals x cubed times the quantity 2x minus 5 to the 4th power. As we're looking at this one is a little bit different than the ones that we have had before because it's not just chain rule, right? I know that this portion right here is going to be chain rule, but it has something multiplied in front of it, which means I'm going to have to do product rule and chain rule on this one. So this one is a product rule and a chain rule, but it's still going to work the exact same way. So here my first function is x cubed, and my second function is the quantity 2x minus 5 all to the 4th power. We're going to follow basic product rule guidelines for this one, which means I'm going to take the derivative of the x cubed first and leave the second one the same, plus the original x cubed plus the derivative, or times the derivative of the quantity 2x minus 5 to the 4th. That's where the chain rule is going to happen. So the entire problem isn't chain rule, just part of it is. So let's go ahead and do the derivative here. When I do the derivative of x cubed, I get 3x squared times the original second function plus the original first function times the derivative of my second function. I'm going to use a bracket here because this is where the chain rule is going to start. So on the second function, my outside function is the parentheses to the 4th power, which means the derivative of that outside becomes 4 times the original inside to the 3rd power. So I dropped the exponent and then decreased the exponent by 1, leaving the inside the same. And then times the derivative of that inside. So what's the derivative of 2x minus 5?
2.
2. Everything in that bracket right there was chain rule. Okay, so that's where the chain rule came in. And now from here, all I need to do is simplify. So as I simplify, we're going to start on the front. Is there anything that I can put together in those first two terms? No, not without foiling out the 2x minus 5 to the 4th power, and nobody wants to do that. So the beginning of this stays the same. But out here on the second term, I have a couple stragglers I can put together. Remember, it's all connected by multiplication. So I can take this x cubed, the 4, and the 2, and I can put all of that together. 4 times 2 is 8, times x cubed is 8x cubed. And then times the parentheses, 2x minus 5 to the 3rd power. And that is as far as I will go on this one. Questions, concerns, or issues? Is anybody still writing this one? Okay, next problem. Y equals 4 times the square root of secant x plus tangent x. Anytime we are given the square root of something, I always prefer rewriting that as an exponent because then it's more obviously a chain rule thing to me and it's easier to work with. So this is the same as 4 times parentheses secant x plus tangent x to the 1/2 power, which makes it a little bit nicer to look at and to work with. This one is not a product rule problem because there's no variable attached to my 4, so I treat it like a constant that's out front. So this is just a chain rule problem. So when I go to take the derivative of this, my outside function is 4 parentheses to the 1/2 power, which means when I take the derivative of that, the 1/2 will multiply into the 4 to become a 2. Everything inside will stay the same. And then I will decrease my exponent by 1, which makes it to the negative 1/2 power. And then times the derivative of my 2 inside functions. So what's the derivative of secant of x? Don't everybody jump in at once?
Secant x, tangent x.
Good. And the derivative of tangent of x?
Secant squared.
Secant squared. And then from here, all I really have to do is simplify. What's the first thing that you probably want to do to simplify this? I'm going to say we want to move that parentheses that has a negative exponent on it so that it becomes a positive exponent. At least that's what I would do. Which means the 2 and the second parentheses stay up in the numerator because it's all connected by multiplication. And then this first parentheses is what moves down to the denominator. And it is to the 1/2 power, do not forget that. What do we notice about my numerator and my denominator?
There's something we can cancel out.
Right, we have to do something first, but we will be able to cancel out one of those factors. So obviously, to me, if I want to make secant x tangent x plus secant squared x into secant x tangent x, I just need to take a secant out of both of those terms in that top parentheses. So when I do that, it just comes out front, and I'm left with tangent of x plus secant of x over my denominator, because that hasn't changed. But remember, this is to the 1/2 power, and this is to the 1 power. So as I'm canceling these out, I'm able to cancel out this entire 1/2, but 1 minus 1/2 still leaves 1/2 as an exponent in that numerator. So what I'm left with now, instead of fully canceling out both of those factors, I was only able to cancel out half of it because that's all I had in my denominator. So now in my numerator, I have 2 secant x times the quantity tangent x plus secant x to the 1/2 power, which of course I can rewrite using a radical. So then this becomes 2 secant x times the square root of tangent x plus secant x. And then that one is as simplified as we can go.
Why could you not take out the whole thing?
Because I didn't have a whole exponent in my denominator, I only had 1/2. So we can only take out what we have.
Oi. Night.
You okay? From here, we just have one more to go. I know it's super exciting, right? We're gonna say yes, yes, it is super exciting. Okay, so this next one is a little bit unique. In the notes, I've done it 2 ways. For the sake of time, we're just gonna do it 1 way in class, but you can definitely compare it to the other way on the notes. So I have the original function, x over the square root of 1 plus x squared. So as I'm looking at this, just like we did on the previous problem, I'm going to want to rewrite that radical as a parentheses with an exponent. So this is the same as x over 1 plus x squared to the 1/2 power even as I'm looking at this, it's pretty clear to me that I have to do quotient rule, which I loathe. Okay, I don't know about the rest of you, but quotient rule just takes forever. Chain rule allows us to get around using quotient rule, which sometimes makes the derivatives a little bit easier to compute. So to get around quotient rule, I'm going to take this whole denominator and I'm going to bring it up to the numerator, just making its exponent a negative. So this is the same as x times 1 plus x squared to the negative 1/2, which is strictly a chain rule problem. Makes it very easy for me to compute it. I'm going to do product rule and chain rule, but it's still really easy. So I'm going to go ahead and color code this like I did the previous product rule and chain rule problem, just so we can see what's happening. So the x on the front is my first function, and the parentheses 1 plus x squared to the negative 1/2 power is my second function. On chain rule, we do the derivative of the first function. So what's the derivative of x?
1.
1 times the original second function and then plus the original first function, x, times the derivative of that second function. So here's where I'm going to use the brackets again, because that second function requires chain rule. The derivative of my outside is the parentheses to the negative 1/2 power. So when I take the derivative of that, the negative 1/2 drops out front. What's inside stays the same. And then I reduce it by 1. Negative 1/2 minus 1 is negative 3/2. And then times the derivative of that inside function. What's the derivative of 1 plus x squared?
2x.
2x. And then from here, I can just go ahead and start simplifying. There's nothing I can do on the front for the most part, except for to rewrite it using a positive exponent. So I'm going to move the 1 plus x squared down to the bottom. So I get 1 over 1 plus x squared to the 1/2 power plus, I can put my stragglers together. So x, 2x, and negative 1/2, I can multiply all together. X times 2x is 2x squared, times negative 1/2 becomes a negative x squared. I can also go ahead then and move this parentheses to the bottom, which makes it a positive 3/2. So now I have 2 fractions. I can't do anything with them currently because they have 2 different denominators. This one is 1 plus x squared to the positive 1/2. This one is 1 plus x squared to the positive 3/2. So if I want to simplify it farther, I need to make them have the same denominator, which I can easily do, right? I can't make this one smaller, but I can make the first one bigger. So what do I need to multiply 1/2 by, or add to 1/2 to get it to 3/2? I need to add 1 whole to it. So I need to multiply both the numerator and the denominator of this first function by 1 plus x squared. In doing that, I get 1 plus x squared over 1 plus x squared to the positive 3 halves, because 1 plus 1 half is 3 halves. And then minus, my second fraction stays the same. Since I now have the same denominator, I can go ahead and combine the numerator and put it over that common denominator. 1 plus x squared minus x squared just leaves me with 1, because the x squares cancel out, over 1 plus x squared to the positive 3 halves power. And that is my derivative. And let me just tell you, if you had done quotient rule, it would have taken twice as long to solve this problem. We are now done with today's notes. Your homework is on Canvas. Of course, I will stay on here for the rest of the class period, which I don't think is super long, but that's okay. And if you have any questions, just let me know. Sound good? Okay.
So can we leave and work on it?
Yeah, you can leave and work on it, or you can stay and work on it.